All right.
Welcome, everyone. This is the International Seminar Series. Today is a special day. We have a dream come true. We have Eric Long talking from San Francisco. He's the Director of Structural Engineering in the San Francisco office. He's got a civil engineering bachelor's in Urbana-Champaign in Illinois, and his master's is from the same university. So thank you very much, Mr. Long, for your time. The room is yours.
All right. Terrific. Thank you for the introduction. It's a pleasure to talk with you today, really about an exciting time in the world of civil and structural engineering. And this presentation today, I think, will highlight some of the reasons why we are so excited to be practicing at this moment in time in our built environment, and really pushing the limits of what we think is possible in terms of not just building tall, but building smart, and reflecting on optimization, efficiency, material use, sensitivity to our environment. All these things are an exciting time to be studying structural engineering. So the presentation I'd like to talk to you about today is in the world of this technology and optimization and what it means to design. Not just can we make buildings lighter and stiffer and more efficient, but how do we do it in a way that is also very meaningful to design? And we have a wide range of these examples, starting the title here, as you can see, from a blank piece of paper, like starting with nothing in terms of concept design, all the way down to final little pieces of rebar and detailing rebar that we can optimize and have this full breadth of opportunity in front of us. So first, I'd like to start with a quick overview of SOM. I'm sure hopefully many of you are familiar with our firm, but just a quick overview. We are a global practice founded in 1936. We have over 1,000 designers across the world. Our big offices are in San Francisco, Chicago, and New York, as well as London, with a growing office in Los Angeles and Washington, D.C. But really from these locations, trying to serve a global practice. We have integrated services, all the disciplines that would be needed to design and a building, including, of course, architecture and structural engineering, MEP, interior design, graphics, planning, landscape, and open space, that all of these disciplines come together, and that we all think of each other as designers, that we all have something to contribute to design. And our firm is rooted in this idea of architecture and structure together as one. Some of our more notable projects, the Burj Khalifa in Dubai on the upper left, then going across the John Hancock Tower, the Jin Mao Tower in Shanghai, as looking up the atrium there, the Cathedral of Christ the Light in Oakland, the church at the bottom left, a Poly headquarters in China, and the Willis Tower, or formerly the Sears Tower, in Chicago. All these buildings firmly rooted in ideas of structure and architecture together, that neither one can be separated. We like to innovate, and we're recognized for being innovators in our industry with numerous awards, whether it's from sustainable systems, plants and things, to the latest energy dissipating devices and seismic fuse connections of this beam column joint you see in the middle top. And that our leadership has been honored with many awards, and almost, we think in terms of our count, a lot a significant number of awards. There's a lot of good architects in the world as well. And perhaps some of the ones that mean the most to us are the 25-year awards, the ones that stand the test of time, that these buildings, even 25 years and beyond after their construction, are still relevant in today's world. And that's really what we're striving for, that when we design buildings, that they're not just relevant for the decade that they're initially built, but they're lasting generations, and they're good buildings for a long time. And what makes them good? What are we looking for in making a good building? First of all, site and context. That we should actively engage, the urban and geography and where the project is, the country that it's in, the culture of its city, and making sure it fits in. This project is in Beijing, where the site was all the residential, office, hotel, retail. We flipped the city street inward out to create this landscape environment down the middle, opening up to pedestrian traffic, what this area of Beijing desperately needed. Another part of our ethos is that structure and system form a primary role. This is the Broadgate Exchange House in London over railroad tracks. And of course, the structure of the arch and hanging the building to avoid the structure coming down on the railroad tracks below was an integral idea to both architecture and structure. And that the shape of the building is integral, that the function of the building and its shape should be one and the same. An office bar, an elongated bar of office space, views out to the river with the core set in the back, all about organizing the building and the shape of the building for its function of office space. And then we should be sensitive to climate and sustainability, that this project in China shaped to gather the wind through the openings in the middle of the building with wind tunnel electric generators to generate electricity for the building, as well as photovoltaics, geothermal systems, one of the first net zero energy buildings in China. And finally, the materiality and tectonics, the fine craft of the details all come together harmoniously to inspire the space and invoke emotion in the design. And detailing tectonics should be very clear and legible, that when you walk in this space, you're occupying the space, things are clear, they're well proportioned, and there's a harmony of the space. One of the last ones is resonance, that when you look at a building, that it should resonate with you as an observer of the building, whether you're outside or inside, and that it respects the heritage and culture and aspirations of the city. So with that little background and kind of the type of buildings and type of designs that we're looking for, how do we as structural engineers contribute to this idea of architecture and structure and these items of our ethos? Technology, we can't help but be excited about it, and I'd like to show you from the blank piece of paper through the individual little pieces of rebar, how we can contribute to this idea. So we think about technology and how technology inspires design. This is the America's Cup sailboat racing. Obviously, the sailboats of the past on the left, and to what technology is doing to these boats to make them go faster, but also that their level of design is so high and well crafted. And technology is really enabling this. And this comes true in not just sailboats, but of course our structures. This is Frey Otto's soap films technology that he used to determine the curvature and shape of the roof of his Munich Olympic Stadium. Whether it's soap films that Freado did, or maybe what we have currently is this tool set and knowledge of technology tools. One of the ones that I'd like to highlight to you today is a commercial software by Altair, this topology optimization, which is in the upper left. The car industry and aeronautical industry uses this quite well to stiffen and optimize frames of cars or fuselage of airplanes, and we're bringing this into the building industry now. But there's lots of tools. We have our own in-house wind tunnel. We use genetic algorithms. We are processing through Grasshopper and Rhino and surface optimization. All these tools are at our fingertips, ready to tackle the problem. But it's difficult to know what tool to use. Design is not black and white. There's a very gray area in between, and these tools really can be used for exploring that gray zone in between and inspiring us to understand design opportunity. What are we searching for in these opportunities? As structural engineers, we're focused on efficiency and cost, of course, but not at the expense of how long it takes to build it, or how complex it is to build it, and how it performs in a wind or seismic event. And of course, it has to be elegant and appropriate as it fits in with the architecture and residents of the building. So some ideas about geometry optimization, these tool sets for geometry. Now we can start with thinking about the John Hancock Tower and that geometry and taper of the tower for wind, and the integration of the X bracing at the perimeter. What's interesting about this building is that 100% of the system is on the perimeter. There is no core, structural core, interior to this building. It is only gravity columns. So the shaping of the geometry was, and the shaping of the X bracing, instrumental in making that happen. The geometry of those braces is very important. Here's a quick little demonstration about why geometry matters. So if we take truss A on the left, truss B on the right, and look at their difference, you might think that A would be better, a simple triangular diagram, but really B is a lot better in terms of strength, 27% more, and in terms of deflection, 60%. So just the same height to depth ratio of the cantilever truss B is far better with simple geometry moves. So how should geometry be measured? Should it just be on structure in terms of proportion for trussing or others? But can we measure this geometry in other factors, such as the efficiency of building floor plates, or the carbon involved in the building, or the solar radiation on the facade, the wider it gets to the top, or how it is affected by the neighboring buildings? All these items can be thought about at the same time that we're thinking about geometry of structure. It's more than just strength and deflection. It's carbon and solar and architectural floor plate geometry as well. So here's a competition that we had in China, where we looked at from a blank piece of paper and thought about the geometry of this tower as it means to structure, and we, as well as floor area and shaping for wind. So we used genetic algorithms here to shape the tower in such that the floor areas were maintained. There was a maximum diameter, a minimum diameter at the base to fit on the site, and how does the tower taper to minimize wind and response of the building while maintaining the requirements of architecture and floor area and solar and carbon. So here's iterative steps along the way that we're tracking all of these things. And in the end, we thought that this was quite an elegant shape through this use of genetic algorithms. So from geometry, we can then start to get into the system. What is the system of a building, the structural system? And so for this example, we'd like to talk about is a bridge example at Los Angeles International Airport, at LAX, where there is this central drive and parking areas in the center, and their desire to have new bridges, 7 of them, extending from the parking central area over to the terminals for each of the 7 terminals. The upper right-hand corner, you see a picture of the bridge as it is today with a simple diagonal box truss expression. LAX decided, can we do better in our welcoming of the passengers to the terminals? So we looked at our background in optimization of trusses, and what we're finding really interesting right now is that when have a cantilever truss, say in a tower or in a beam, as an example here with this red arrow down on the beam, that the X bracing, the midpoint of that, the intersection of that X is not at the midpoint of its bay. It's pushed up. Can you see my cursor moving? When I move my cursor around, I'm not sure.
Yes, we can.
Okay, so seeing this example bay extruded here in the middle, you see that this mid-height node here is not exactly in the middle. It's 3/4 height. It's an optimal location for this for the brace angles. And so we thought about this bridge as it expands from the parking garage over to the terminal. This is an elliptical shape, thinking about a tubular structure, and using the Altair and topology optimization to understand the natural force flow of material on that particular shape. And what we're seeing is that these truss lines intersect at that same 3/4 high space in the bay. And so we interpreted that diagram, thinking about it in elevation, thinking about it as a kit of parts. How could we build it? How could we prefabricate units, bring them together, and with simple nodal connections that are repetitive? And then what it could be as an expression and an experience traveling from the parking garage over to the terminal. So from the system, from the structural system to the components of a system, how can we think about designing components of a building that are expressive, that are efficient, and that are rooted in these fundamentals? This was the This is the Los Angeles Federal Courthouse, a new project recently completed construction last year, where the idea of this building was to have an elevated cube, a civic proportion to this courthouse elevated above the ground level to allow the sloping topography of the site to pass underneath, as well as to give it a grand civic courtyard and an entry space at the sidewalk and underneath the building. So the challenge here is, how do we suspend this cube and lift the building off the ground? So the building plan looks like this, where we have in blue is the shear wall cores, concrete cores that extend from foundation all the way up to the roof. And then we have hanger columns around the perimeter. So we're going to take the shear walls up to the top. We're going to have a truss element at the top go over and then hang this red perimeter frame from those trusses at the top. An example diagram on the left where our shear wall cores rise up to the top with a roof hat truss and our hanging columns taking the load up, over, and down to hang the columns and suspend the cube above the plaza. So how do we do this roof truss? This was a first pass at our roof truss design, a simple diagonal component where we took the bottom, this ball here as the bottom cord in compression in blue, the very top of the roof and the tension cord in red. So red in tension, blue in compression to hang this perimeter column. But we thought about, can we do better than this? Is there more interesting geometries that are more efficient, better use of steel, better deflection, perhaps? So again, thinking about this topology optimization, we used setting up a three-dimensional roof truss space that allows the topology optimization to determine where the material should be in order to be most efficient. And of course, we saw this triangular form a little bit different than our initial configuration. So we were interested in that, took that into 2 dimensions, and looking at that, and we thought, wow, what's really happening here is when we have supports on the left and a hanger load on the right, that we're really getting this bicycle wheel type of truss where this compression ring wants to form up and over, and these tensile spokes come back down to the middle. This white space here is a required door opening for a corridor architecturally. So we can even include that and let the optimization flow around even required openings. And so what we determined is we flipped that bicycle wheel actually upside down and used it in the geometry on the bottom, where we have this bicycle wheel in compression and these tension spokes in red, and determined that this was saved 14% in steel material and had better deflection performance as a result of this bicycle wheel approach idea. And here it is in its built form. Here's a drone shot under construction with the tower going up, the steel truss, and this top floor. If you notice in this image, we still have the shoring columns. So we had temporary compression columns at the bottom, allowing these columns and floors to be erected in a conventional bottom-up approach, connecting the roof truss, making the welded connections, and then pulling out the shoring column at the bottom to transition the load in the column from compression into tension, and the load goes up through the truss and back down the shear wall cores. And it's successful. It was a moment of truth when those shoring columns were pulled out, and we're happy to say that the amount of deflection and as anticipated was within 1/8 of an inch, or within 5 or 6 millimeters of what we predicted. So now, lastly, to the detail level. How do we think about this use of technology and component all the way down to the individual details? For this project is 350 Mission in San Francisco, an office building which has a central shear wall core, perimeter columns, except for this corner column here. This intersection where this photograph is taken is a prominent intersection of the city where pedestrians are walking by this corner at all times. And so we opened up the lobby of this building to be a public lobby eliminated the corner columns so that it invites passengers and pedestrians to enter the lobby as they cut the corner as they're walking by, stop at the coffee bar or something to welcome them into the building. But how do we think about this floor plate with a missing column as well as a long span for office space from the core to the perimeter? That long span is 43 feet, or in meters, maybe 12 meters or so, 12, 13 meters. And what we would conventionally think about for office buildings for that span would be steel beams. But here we thought about concrete and the use of flat slabs, no beams, and to have an raised floor system where all the mechanical and electrical systems are run, such that giving office space complete floor to ceiling, full height, 10 feet 11, or I say almost 3.5 meters or so, with floor to ceiling glass and its view out to that prominent intersection over the city. So how do we think about post-tensioning, PT, inside of a slab as for a particular support condition of the core and the columns? We thought about this optimization to understand the lines of optimal material placement spanning from the core to the perimeter. And you can see that we were inspired by this and placed the lines of post-tensioning in the floor to correspond to this diagram. And the result is this, that we have this long span flat slab with no beams, exposing that slab to the occupants of the floor. The raised floor system, the mechanical system, will come in here on the floor level and extend out over the top of this upturned beam. This upturned beam was room for additional stiffness and additional post-tensioning to reach out to the corner for the missing column. You can see the ductwork included in here, so the mechanical system can plug into this, go through and supply the fresh air to the perimeter slot diffuser along the window wall. Here the building is under construction. And lastly, a thought about this optimization of post-tensioning was really interesting. And the next project that we applied it to was this 75 Howard, a residential building in San Francisco, where we spaced the locations of columns and core with high regards to where the units, residential units are, placing the columns as thin wall-like elements between the units, such that the units themselves have uninterrupted space and the columns are buried in the wall. Except for the corner. The corner column we pulled back from the corner into the central part of the unit and had a tapered, this section here in the middle of this more orange, peach colored unit, the corner units, has a shaped column capital, a shaped slab that allows it to cantilever the extra distance when we pull the column back towards the interior of the space. So we looked at this optimization again for our column locations and supports, where the optimal placement of material would want to be. And then we overlaid trace paper on top and started to sketch. Well, what's interesting is these lines are not straight necessarily. These lines of optimization are highly curved. So should we curve the post-tensioning around and follow these lines? We found that if we do this, we save 25% of the post-tensioning material required and had better deflection performance of our slab. Here's an interior unit. Look, with this column pulled back, helping to define the dining room space, the living room space, and the kitchen. This tapered column capital as a design element in the space with the column and its views out to the San Francisco Bay. Pulling these columns back, whether they're in the unit above or in at the corner, allowed for these opportunities to recess the glass back and make these open terrace levels that have indoor-outdoor California living. So that's what a thought about our design, stemming back all the way to our historic and notable structures like the John Hancock Tower and Sears Tower, our ideas rooted in architecture and engineering, and pulling that forward to today and opportunities using technology to help inspire us about whether it's an overall building shape or a system or a component, or even down to the layout of post-tensioning in a slab. There's opportunities for design in all levels, and we are all designers. So thank you for your time.
Mr. Long, thank you for the presentation. And I would like to ask people attending the webinar if there's any question or questions that I should ask Mr. Long, so you can write them on the chat, and then I'll pass the questions to him. In the meantime, I have a question for you, Mr. Long. How long does it take topology enhancement, since the moment you decide to start doing the optimization, the numerical optimization, how long does it take for a computer or the computer you use to come up with an optimal, an optimized solution? How long does it take?
So the computer, that's a good question, Federico. And I think the answer, of course, it has to be a little bit mixed. But let me just use an example. The 75 Howard post-tensioning optimization here, that's in the middle left-hand image. The optimization itself is very fast. We could do that in a half of a day, setting up, we know where the columns and core were. We can set up that model, bring it into HyperWorks and OptiStruct with Altera software. Very easy to bring it in and run that. The more time-consuming part of that is actually now our job now is, as humans, to lay trace paper over the top of that and determine how to interpret that diagram. We don't take the diagram necessarily literally. We have to interpret it and thinking about construction and layering of components, how it goes together. So that could take, a few more days, of course, or even weeks to continue to think about that and use the optimization as inspiration for the design.
And absolutely, I understand. So the worst is to actually get with a physical solution based on the topology diagram, the optimized one.
Right.
All right. So anyone
is that even in competitions where we're going after projects or very early on in the design phase of a project where we're still just exploring, we can run these optimizations very fast and use them as inspiration tools with our architects as well as engineers to interpret the diagram.
All right, thank you. I have another question, and it is a little more regarding to fabrication. When you come up with these very complex solutions, geometrically speaking, where you have, for instance, in the Los Angeles pedestrian bridge, where you have all these pipes that they go into crazy angles and things like that. Have you felt like any increase in construction or in creating these special shapes out of the mathematical approach?
That's a good question, and of course that's what we think about when we have different shapes than what we may be used to seeing, we as well as the contractor will think about that. Well, what does this mean? How do we think about this in a different way that allows construction and fabrication to be similar and perhaps maybe even better than a conventional system. And what we, as I talked about in the LAX pedestrian bridge example, is that all of those nodes are actually the same geometry. Those angles that they intersect are the same and repeated along the length of the bridge. So can we prefabricate these in modules such that they can be put on a truck, a semi-truck, brought to the site and lifted into place, and simply with simple connections to connect the modules and complete the truss. Interestingly, you see the diagram on the middle right. This bridge is over many lanes of traffic, so you can imagine this traffic and road needs to stay open to allow passengers every day to enter the airport. So in fact, this modular system of this truss was a good idea in that we could prefabricate it and bring it in overnight and connect it together while still keeping the traffic and the lanes open below. So I think, you know, we have to continually think about even complex geometry as opportunity to even solve other problems, like keeping the traffic open to the below.
Okay, thank you very much. I'll ask for the last time, do we have any other questions on whoever is attending online? Okay. Well, I have a question from a student. He's right here with me on the room. He wants to know if you know, what is the software you're using for this mathematical optimization?
So the topology optimization examples that I showed are used with Altair software. It's called OptiStruct, HyperWorks and OptiStruct. We use both to do this optimization. They are a great partner of ours in this work, and we are just super excited about this technology and its opportunity and where this goes in the future.
I have a question, Mr. Long. They ask, Isaac asks, are all the tools proprietary, or if there's anything open source that might be known to everyone and that we can use to explore?
Yeah, there's lots of opens. Well, they're both. Some of the tools that I showed in that big chart are written in-house by SOM or just SOM institutional knowledge, but many of them are open source and available to others. I think a good example is the genetic algorithm tool. I know in Rhino and Grasshopper, I think there's a Galapagos plugin for Grasshopper that has a genetic algorithm and structural calculation tool built into it. That's open source, and many people use that currently for genetic algorithms.
All right, that's all there's to it, Mr. Long. Honestly, thank you very much for making this happen. I really appreciate it, and I hope I can count with you in the future for future seminars like today. It's a great opportunity for everyone attending, and especially for the master's program of Javeriana University. Thank you very much.
You're quite welcome, and thank you again for having me, and we look forward to our relationship in the future.
Thank you, sir. Have a good day.
Okay, bye-bye.
Bye-bye. A todos, muchísimas gracias por atender el seminario. El video, cuando lo tenga procesado, lo montaremos en la página de la universidad, de web, en el YouTube que tiene la maestría para esto. Muchísimas gracias.